career with the ICME community. So thank you again for joining.
Oh, thank you so much for the introduction, Gianluca. It's so nice to be able to give back or to be engaged with ICME in any capacity that I can. It's been amazing to see how the program has expanded and become this juggernaut or powerhouse since I graduated. And I'll say, yeah, I actually have a very keen interest in seeing ICME alums get placed in the academic job market. So if anyone wants to reach out to me in any capacity for help on looking at your statements of purpose or whatever it is, do please let me know. I think our department at USC could really use some of the technical chops that you all have. So I have a very strong vested interest in trying to make that happen. So I'd love to make myself available for that. I have a picture here of some hexagons that are in kind of a vortex, if you will. Let me ask here if you want to chime in. Does anyone recognize this picture? You can type it into chat, or you can unmute yourself if you like. I'm curious if anyone, this looks familiar to anyone. I guess not. So this picture is actually hanging in Huang. If you're looking at the entrance to the ICME wing and you look up and to the right, this is part of a collection of pictures that are posted up there. And this is kind of related to a paper that I wrote, or well, it's kind of related to the topic that I'm going to bring up today, which is called the continuous approximation paradigm. This comes from a paper that I wrote in 2012 that I also wrote a story for Siam News for in April 2016. So it's a fun little piece that I wrote. So next time you're in Huang, have a look up and to the right, and you'll see this poster there, and it comes from this thing here. So anyway, what I'm going to be talking about today is what's called the continuous approximation paradigm, which is a subject that let me full screen this. There we go. It's a subject that I was introduced to here when I was a student at Stanford. I did my PhD with Yin Yu Yi. And it's a subject that in my view doesn't get a lot of attention, but is something that really appeals to, it has a lot of mathematical appeal to it. I'll put it that way. It's easy to prove theorems, and it's easy to derive results that are actionable, or it's easy to sort of understand problems in a very broad scale. Something I happen to like quite a bit. And I think that if we had some ICME talent that was investigating this research field, you'd be able to do a lot of great things. So I'll describe what this is. The continuous approximation paradigm is a way of looking at logistics problems like the traveling salesman problem, or P medians, minimum spanning tree, logistics problems on networks, where you're trying to decide where to put things or where things should go. And you reason about them geometrically, as opposed to thinking of them as being imbued with a network structure. And so Carlos de Gonzo, who recently retired from Berkeley, is someone who is strongly associated with this field. And the idea is that, the quote here, detailed data are replaced by concise summaries, and numerical methods are replaced by analytic models. So rather than study branch and bound approaches for solving a vehicle routing problem, instead you say, well, let's pretend that my demand was distributed, according to some probability distribution, and let's just study asymptotic behavior, or let's try and come up with some estimates for what the objective value of these problems looks like. So I like to think of this whole subject as being like the operations research equivalent of what's called Fermi estimation. I didn't know this was the name for it. This is something a lot of us learn this in physics classes, I think, when you're looking at sort of order of magnitudes that you're trying to estimate, some complicated quantity, and you want to reason about it just using sort of back of the envelope calculations. So here's an example of a Fermi estimation problem. You might ask, how many piano tuners are there in Chicago? Okay, I have no idea what that number should be, right? We'll try and just guess it based on what information we might have available to us. So it's not hard to figure out that Chicago has about 3 million people in it. And you could say, okay, well, let's say an average has about 4 people in it. And so give or take, the number of families in Chicago is about 750,000. And we'll say, well, how many families own a piano? Say maybe 1 in 5. Okay, why 1 in 5? Well, it's as good a value as any. It's probably more than 1 in 50. It's probably less than 1 in 2. So let's go with that. That means, okay, about 150,000 pianos that are sitting there in Chicago. And we'll say, all right, let's assume that a piano tuner on average tunes 4 pianos every day of the week. That sounds a little bit high. Piano tuning takes longer than that, but that seems like a good number. 4 pianos every day of the week for 5 days. And they rest on weekends, and say they take a 2-week vacation every year. And you'd say, okay, how many pianos is this tuner tuning every year? About 1,000, because you have 150,000 pianos, and you have 50 days of the week of the year. And the piano tuner tunes 5 days a week, 4 pianos a day. And that would say, okay, based on just the unit analysis of all these numbers that I pulled out of nowhere, there should be about 150 piano tuners in Chicago. Okay, and if you Google it and do some looking into it, it's about 300. So I'm within a factor of 2, which is not terrible. And the important thing is I didn't use any, significant information. I just made a bunch of guesses, and I came up with an estimate that was not totally ridiculous. So the continuous approximation paradigm is doing this, but for things like the traveling salesman problem. Okay, so this is, we're going to ask the question, what happens if I sample a lot of points, let's say uniformly in the unit square, and I compute the length of their TSP tour? So this is me sampling 100 points, and the tour looks like that, and the length is 7.624. This is me sampling 200 points, and the length is 10.6. And then this is 500 points, and the length is 16.617. Okay, so let's say, all right, what, these are random variables. They're random quantities, but let's see if we can say something about it, right? What roughly speaking do these numbers, the pattern do these numbers follow? Just curious here. Does anyone happen to know what the scaling is of the traveling salesman problem? I'm guessing the answer is no. This is kind of an esoteric thing, but I'd love to, if anyone's familiar with this theorem or anything, I'd love to know. I suspect not, because it's really a very, in my view, understudied sort of thing. So the result is actually goes back to 1959. It's called the Beardwood-Halton-Hammersley theorem, usually just called BHH theorem for short. And it says if you have a sequence of independent uniform samples in a compact region with area 1, I did the unit square, that doesn't matter, then here's what's true. With probability 1, if I take the length of the TSP tour and divide that by the square root of the number of points, that limit with probability 1 is a constant. We don't know what that constant is. We know it's between 0.625 and 0.9204. The best simulations we know right now are due to David Applegate at AT&T, who says it's about 0.7124. And I think his arguments are pretty compelling. So why does this help us? It tells me that I can predict the length of a TSP tour as being, roughly speaking, this constant, which is about 0.71, times the square root of the number of points. I'll fire up MATLAB and show you. Let's take, is anyone willing to shout out a number between, let's say, well, let's do this one step at a time. Anyone, if you like, post it in the chat or just shout out any number, let's say between 200 and 2000. Just shout out a number and we'll work with that. You can punch it in the chat. I'll grab the first one I hear. 847, says Nathan Staffa. Okay, thank you. 847 will be the number of points. So N will be that, and I'll say X will be a random set of 847 points. So let's do one. You can see here's 847 points. So this theorem says that if I want to know, roughly speak, I'm about to take a traveling salesman tour of these 847 points here. This theorem tells me that a good estimate I can get is the following. So beta is this constant that I mentioned before that we know exists. And I'll use this Applegate estimate of 0.7124. And the prediction is that I can say, well, I think that length of the traveling salesman tour of all these points will be about beta times the square root of n, which is 20.7. Okay, that's the prediction for the length of this TSP tour. Now I'll actually compute it. And, traveling salesman is NP hard. So I'm actually going to use the Lynn-Kernighan heuristic. The Lynn-Kernighan heuristic really, really well. And so I hope you don't think I'm cheating there. So I'll hit enter. We'll there's the torr that it looks like, and it says 21.79. So I'm off by about 1/20th or slightly less than that. So not a bad estimate. And that's what the continuous approximation paradigm does. It lets you predict these kinds of quantities. So let's see, Aditya asked 1986. Let's do that too, just for fun, really quick. I'll do the exact same thing I just did. We'll do 1986. And the prediction is 31.74, and the length is 32.64. So again, pretty good. So that's the Beardwood-Halton-Hammersley theorem. And it doesn't require uniformity, actually. It's a theorem that works even in the non-uniform case. The statement works like this. The change now is that there's a new factor that you have to integrate, which is the integral of the square root of the density, which is kind of neat. So the integral of the square root of the density is something you multiply this whole expression by. And that's how you can predict that. So I also could have predicted that TSP torr for the uniform case as well, for the non-uniform case as well. It also works in arbitrary dimensions as well, which I don't think I need to get into too much here. It's it looks like that too. It also works for the p-medians problem. So for the p-medians problem, I have 100 points here on the left, and I did 500 on the right. And I sampled, in this case, 7 medians here on the left and 35 here on the right. So I set things so that the number of medians would be 0.07 times the number of points. And if you do that, there is a theorem that is similar to this as well that says you have this kind of square root scaling. That's due to Dorrit Hochbaum and Michael Steele in 1982. So there's a lot of these things, and we've been working on some extensions of those and applications and trying to actually make use of these things in industry beyond being pieces of beautiful mathematics. Really quickly, I'll share the intuition for where these formulas come from. If I've got n points in the unit square like this, here's one way of building a torr. Let's just zigzag across the torr m times, where m is my choice. M is something I can choose how many times I zigzag. Okay, zigzag back and forth like this, and move up and down, kind of stripe that square, and then make little detours like this to visit these extra points. So how much work? And if I do this, I've now got a torr that visits every point. And how much work have I done? Well, I zigzagged across this thing m times. I went up and down the height of this unit square. That's a 2. And then for each one of these little detours here, the amount of work I did was n on m. And so therefore, if I optimize this with respect to m, minimize it, the optimal solution looks like m should be root n, at which point the solution is 2 root n plus 2. So that's a quick way of sort of back of the envelope working out that things should scale proportionally to square root of n. Okay, so that's the continuous approximation paradigm. So one of the things I like to do is to study modern logistical problems and try and come up with theorems of this sort for problems beyond TSP. And so I'll do a couple of examples in this talk here. The first one is, we call it sidekick routing. It's also called horsefly routing for reasons I'll explain in a minute. This refers to a logistical system where you have a big truck. I like this Mercedes one here the best. This one, you have this big truck here. That's not a big truck. It's an electric van. And you'll see it's got 2 drones on top of it. And so what this is called the Mercedes Vision Van. And it's a van with these 2 drones. And the idea is that you would deliver packages with this thing. This truck would be driving, or this van would drive through a city, and you'd have drones that are picking up packages from the van and then dropping them off at customers, and then coming back and retrieving them and retrieving a new package, and so on and so forth. So the van doesn't actually have to stop at your house. Right. The van doesn't have to stop at your house because the drones do that bit. The van can do some clever path that is, we hope, shorter, and thereby get the packages to you more quickly. So that's the Mercedes Vision Van. This is one by a company called Starship. This doesn't use drones. It uses a robot on the ground, but the principle is still the same. You have a truck that's driving along. That's this like mobile launch pad for these, what we call sidekicks, hence the name. A horsefly is what you usually use when you're talking to drones because, it's flying. Which is over here. So BoxBot, I think, was acquired by Amazon. No, Dispatch was acquired by Amazon. This one here comes out of a Berkeley company. This is called Kiwi Campus, which I think might have had some financial troubles recently, which is unfortunate. But they used to at least deliver food within the Berkeley metropolitan area. And they had these tricycles that someone would ride. And then this robot would come out and intercept the food product and then go to your house. So that's the idea. This one here is called the Workhorse system. It's based out of Maryland. So the solution, I think this picture here conveys this pretty well. These dots here would be your customers, the people that need packages. And then we'll say this square here would be where your truck starts. And so this is one example of a solution. The truck would drive along this thick line here. And as the truck is doing that, you've got this dashed line here, which is the path of the drone. And so this would be a drone going back and forth between the truck and these customers, dropping off these various packages, and then eventually rendezvousing with the, well, it alternates between dropping the package off and then retrieving a new package from the truck like that. And what's nice about this, well, computationally, there's very little that's nice about it, with the exception that when you fix the sequence of events, actually the problem is convex, which is kind of nice. So I've written it here. Let me erase what I've just drawn here and talk a little bit about this. So the way we thought about this is we said, let's try and minimize the amount of time until you return back home and you've delivered all of these packages. And so what does that mean you need to do? It means you have to choose these launch sites, right? It means geographically I need to choose where I'm going to release this drone. And so what do I need to choose? I need to choose a permutation, the sequence of launches, right? When do I launch for which customer? And then for each customer, I have to choose the launch site. And then I do that, and I want to minimize this objective function here. And this objective function is the sum of the maximum of two things. Now, what is this that we're looking at here? Let's look at this picture over here on the left. So you'll notice here, what does this look like here? This models a case where the truck is here. It releases the drone, which leaves and drops off the package, and then rendezvous back here. And the truck moves like this, and they meet up again. So what does this objective function mean? It means you're summing over every customer that you have to drop a package off to. And you've got this term here, which is the maximum of two things. And what is this? Let's have a look at that. This event here, so this is, I'm going to say that phi naught is the speed of the truck. Phi 1 is the speed of I'm calling it a sidekick of the drone. Okay, so 1 on phi naught times this thing times x of sigma I minus s to sigma I plus 1. That's the amount of time it takes for the truck to get from here to here. Okay, that's how much time it takes for each truck to get from one location to the next. This thing here, this is 1 on phi 1, which is the drone speed, times the x going to the p, and then the p going to the x, which is this thing up. Let me erase that again, which is this bit here. There it is, like that. And so since the truck and the drone have to rendezvous with each other, you have a sum of these components like that. And if you fix the permutation, then this becomes a second order cone program, which is nice and easy to solve. That's like the only nice thing about the tractability of this problem. It's just miserable otherwise, which is really disappointing. So you can also write this using some sort of constraint programming type expressions. If you have more than one drone, if you have K drones here, I don't want to emphasize this too much because I have nothing useful to say about it. It's not at all tractable. I'm just writing this out so that we do have a formal way of describing this problem. And then you could ask the question, well, is the truck allowed to visit the customers at all, or is the truck not? So either you're forbidden from visiting these customers, or you're allowed to, and that affects some of the problem formulation there. But again, that's not really. I don't want to emphasize too much of that. So the first theorem I'll present here, this is a paper we published in Operations Research a couple of years ago. We tried to come up with our own equivalent of this Beardwood-Halton-Hammersley theorem, but for this sidekick routing problem. And the theorem here is a mouthful. Okay, so I'm not going to go too much through that. This is the statement of the theorem. On the next slide, I've got an explain like I'm 5 type expression here. And if you use Reddit or whatever, you might know that term. So what did we manage to prove? The Beardwood-Halton-Hammersley theorem says that if I just take a traveling salesman tour, so if I don't have any drones at all or no sidekicks or anything like that, I just have a truck that's going along and dropping packages off, that the proportionality looks like this. Remember, I said square root of n is one term, and then you'd have to multiply by this constant 0.7124, which I've kind of set aside. And then what would be left? Well, you're using a truck to do all these visits, and so you would divide by the truck speed. Okay, so I'd say, well, if I had no truck, if I had no sidekicks, no drones at all, I know that the amount of time needed to do all this would look like that. We've proven a result that says that when you have these sidekicks, and I'll sketch the proof in a moment, that rather than look like this, the scaling looks like this. It's 1 over, again, there's a root n over there, and then it's 1 over the square root of this thing here, of phi naught times the maximum of phi naught and phi 1 k. Now, k is the number of sidekicks that you have. Phi 1, remember, is the speed of the drones or robots on the ground. And then phi naught, once again, is the speed of the truck. So we have our own proportionality that we've derived. And what this lets us do is it lets us predict what the improvement is going to be if you're trying to decide between should I introduce sidekicks or not. It says that if phi 1k is greater than phi naught, then we know that which of these terms is in that max over there. And then the ratio of the speed with sidekicks versus no sidekicks, just divide these terms out and you get that. So you take the ratio of the truck speed on top, divide that by the drone speed times the number of drones, and square root that whole thing. So we now have a way of predicting, here's how much, based on probabilistic reasoning that I'll get to in a moment, we have a way of predicting how long we expect these tours to take. And something else I would say that comes out of this is the nature of our expression kind of tells us, and again, I should be more precise about what you actually get, but for interest of time, I'm just hand waving a lot. Part of our analysis tells you that this is the quantity, that these are the two quantities that you really want to compare. In other words, if it happens to be the case that phi naught, the speed of the truck, is, greater than phi 1k, which is the speed of the drones times the number of drones. If that were true, then that tells you, well, these sidekicks probably don't help you very much. And so part of what this analysis does is it tells you what the right sort of quantities are to look at, right? That it's the speed of the truck versus the number of drones times the speed of the drones there. So this tells you, for example, if I have the robots, for instance, if I'm using robots and not drones, presumably those robots are not as fast as my truck is, right? Because my truck can cruise along at 20 miles an hour or whatever it is, and the trucks are probably moving at walking speed. Sorry, the robots are moving at walking speed. But if I have enough of them, then that makes k larger, which means this term starts to outperform that one, which is kind of neat. So I'll explain a little bit about the reasoning behind where we get this. So I'll describe an upper bound with zigzagging, and I'll say, let's suppose you have uniformly distributed points like this. I give you a bunch of points here on the left, and I say, okay, you have, let's say, 3 sidekicks available, 3 drones. So come up with something reasonable here. Come up with some reasonable tour that visits all of these things. So what you can do, and what I've done here on the right, is I've first partitioned these points into a collection of rectangles. And then I've described a tour where my truck moves along and it zigzags 3 times across each of these rectangles like that. So the path that my pen is tracing now is what a truck would do. And so you have 3 drones. And so what is my truck doing in each of these? I'll do this one up there so you can see most easily. What happens is my truck, I'd be coming from this direction, I guess. My truck moves along here, and whenever it's aligned with one of these customers, it releases a drone. So the drone leaves to visit the customer and then comes back. And so my truck does this, it releases these 3 drones, and then it moves back to where it came from. And now it moves back one more time and it retrieves all of those drones on this last leg back. And then you do this everywhere. So all I've done is come up with sort of a simple common sense way that you might use these drones. And if you study the limiting behavior of this, if you study how well this kind of policy performs, you get this quantity here. You get 2 root 3 times 1 over phi naught phi 1k times root n. Which is the proportionality that we would be looking for that would be consistent with the prediction that I that I made up there. There's no max term over there, but the reasons for that are not so interesting. So that's how we come up with an upper bound. And then you can ask, how does that work for non-uniform distributions? Because we had a result for non-uniform distributions as well, which is of the same flavor. And you basically take that zigzag and you just stretch or sort of dilate it to be kind of commensurate with the actual density there. So these are some points sampled from a probability distribution, and then I've got zigzags that look like this, and the quantity behaves as you would want it to. So I made this statement, I made this theorem about the proportionality. I've proven an upper bound that is consistent with that, and it's a pretty simple one based on a very simple routing kind of strategy. The lower bound requires that I invoke some of these earlier theorems, the Bearded-Halton-Hammersley theorem for the TSP and the p-median solution from Dorrit-Hochbaum's paper. And that looks like this. It tells me that if I can solve this problem and the objective value is opt, okay, whatever that is. So I solve this problem. It says, if you can find one like that, then there is a TSP Tor whose objective value looks like this. This is phi naught plus k phi 1. So phi naught, again, is the speed of the truck, and k phi 1 is the speed of the drone. So where this is useful is that I already know how the TSP scales, and I also know how the p-medians problem scales. And it turns out that I can use those two results as lower bounds that limit how good my problem of interest, my sidekick routing problem happens to be. So I can say, okay, what's the probability that I can get a really, really, really good sidekick routing problem solution? And you'd say, well, if you can get a sidekick routing problem that is amazing like this, then you would have to either have also a TSP solution that had an amazing objective value, or a p-medians solution that has a good objective value. And I'll sketch that really quickly here before doing the computational experiments. By the way, in case there have been any hands raised or anything, I think I've hidden my window, so I'm more than happy to take any questions if you have any, as I pull up my little notepad here. So please feel free to just jump on in if you have any questions. It doesn't even have to be about research. I love just talking about ICB in general. And oh, my Bluetooth pad disconnected. Bear with me for just 1 second here. If it doesn't work, it doesn't work. That's no big deal, but I would love to show this picture. Did that get it? Okay, great. So it looks like this. So let's suppose I have some customers, and then I have a horsefly torque. Let's make this really simple. My vehicle goes like this. And we'll say I have, we'll just do one drone. We'll make things really easy for myself. So my drone just alternates like this and goes back and forth to these various customers. So you can look at this and I'll say, okay, there's a way of taking this solution here. Let me make the truck thicker so you can distinguish between what's what. I'll say, well, there's kind of an obvious way of taking this picture and creating a TSP Tor out of this picture, right? All you would have to do is you would just take the, I'm going to draw even thicker now. You would just basically glue these two Tors together. You'd have the Tor do the work of both the drones and the truck. So I'll start over here like this, and I'll say you would just move like this, and you'd move along this Tor like that, and like this, and so on and so forth, right? Just glue these two Tors together, and then you would be able to visit both of these. And so that lets you make a connection between the sidekick routing problem and the traveling salesman. Now there's also a connection to the k-medians problem, and I'll sketch that one here too, like this. So here's, let's say this is our vehicle Tor like that, and here's our Tor that the sidekicks do. Oh, I missed one of the customers there, but here, I'll put that over there like that. Now I'm claiming that if you've got that, there's a way of using this solution to the sidekick routing problem to construct a solution to the p-medians problem. And the way you would do that is basically you would cluster consecutive points together on the Tor, and then you would find, say, a median for these things and then assign them like that. So that's how our lower bound works. We say, well, we can show that if you can produce a solution to this problem, then there's a way of producing a solution to both the TSP and the p-medians problem. And since we already know the convergence analysis of the TSP and the p-medians problem based on these other theorems I mentioned, you can conclude the bounds that you want for this problem here. So we did some computational experiments on a road network in Pasadena. So this is a map of Pasadena here in the upper left. And then I took census districts here in the upper right, so little dots, the centers of the census parcels, I think they're called. And then I sampled, I think, 30 of them here and took a TSP tour of them. And clearly there was something funny going on with traffic because this intersects itself a lot more than I would expect a TSP tour to. And then here on the right, I showed the picture of a tour using, we wrote our own little heuristic for solving these sidekick routing problems on a road network. And so that's what you see here. So you'll notice the van is driving, the thick line here is driving a lot less in the bottom right than on the bottom left. And the drone is taking up a lot more of that slack there. And so what we show in this chart here, there's a lot to take in. So we've got 3 columns and 4 rows. For the 3 columns, we've got the number of customers that you have to visit. We call that N. It's either 25, 50, or 100. And then we tried various speeds of a drone. So we tried from 30 up to 60. The truck speed, of course, is just induced from the road network, right? You can get that. So we didn't have to make any assumptions about the truck speed. That comes from the data. And then we plotted here as we said, okay, the black bars for all of these represent how much time it takes you to visit all these customers without using drones at all, just a vanilla TSP tour. And then the gray bar represents the prediction of how much, based on this analysis, you expect things to improve by. And then the white bar represents what we actually came up with when we ran the heuristic. So that the metric of how good my predictions are is how close the gray and white bars are to each other. And I've been kind of sneaky by making them really small, but if you look at them carefully enough, I think they're pretty good. Okay, this one's not so great. But overall, if you look at the gray and the white bars, they're pretty close, which indicates that our prediction is a pretty good one. One thing I learned at ICME is that, the real test of any engineering is, does it enable you to predict things, right? We're very data intensive type people. And so if I'm going to present you a formula, I've got to actually show you something that explains why it's useful and that I can actually predict things well. Future work along this I've got another set of problems we'll look at in a minute, but future work for this one. In this problem here, I assumed that the sidekicks could visit each customer once, like they had a capacity of 1. They drop off a package, they'd come back to the truck, they drop off a package, they come back to the truck. But there's no reason you shouldn't generalize that and say, well, what if you have a big drone that can hold 4 things at once? How would that affect this model? I also didn't take into account capacity of the truck. What if the truck has to return to the depot periodically? And what happens when you have battery life of these drones as well? I haven't touched that at all either. So a lot of future work to be done there. I have only a few minutes left, and I want to talk about selection routing problems. So a selection routing problem is a routing problem like traveling salesman, vehicle routing, this kind of thing. And this is a term that Joe Mitchell at Stony Brook has kind of invented the last time I spoke with him. This isn't sort of an official designation. And this is just what we're using to call the family of routing problems where you don't have to visit every point that is given to you. So maybe instead of having n points and you have to visit all of them, you have n sets of points and you have to visit one member from each set. So we thought, hey, you know what? There are a lot of these kinds of problems out there. I've got 4 bullet points here, which I could talk about. A lot of people have looked at these, but strangely enough, there aren't sort of BHH type theorems for them. Like no one actually worked out what the right scaling is. And we thought, well, this seems like kind of a good opening. And I should say, if you're at all interested in this line of work or in what I've talked about so far, there are just tons of other problems that don't have these kind of formulas that you could analyze that way. There's a whole laundry list of the variations I can think of. So if this excites you and you're interested in working on this, send me a message and I'd love to share some of the kind of open problems that I think are very tractable, very doable, especially for ICME people who are already inclined towards all kinds of all kinds of deep mathematical thinking. So let's talk about this one. This is called the one of a subset TSP. So what this is here, I've got 24 points, 24 numbers here that I've drawn. And each number appears 4 times. Like this is, I wrote this as x4. The number 4 appears 4 times. And in the one of a subset TSP, you don't need to visit every point, but you want to visit each set exactly once. So as I said here, all the numbers, these are all numbers 1 through 6. Each number appears 4 times. And this tour is the shortest tour that visits one of each number. So this tour here has 1, 2, 3, 4, 5, 6 on it. And this is the shortest tour that does that. So this is the generalization of the traveling salesman problem, because it's not just visit all these points. It's you have to select which point you're going to visit. The application that motivated this is something called random Stow. I did some work with JD.com, which is this gigantic retailer in China, and the team that worked on that was just nominated for the Edelman Prize, which we're very happy about. And they are interested in something called random Stow, which Amazon already uses to great effect. It's very efficient for them. Random Stow is a system in warehousing where you don't organize your stock. You organize your SKUs, as they're called, stock keeping units, SKUs. You just throw them randomly on the shelves. And so this picture here would be an example of not random Stow, because I've got these various items indicated by these various pictures, and they're all co-located with one another. So if I said, okay, you need to go into this warehouse and get me a star and a square and a hexagon and a nuclear symbol and then come back, this would be the shortest tour that does that. It's called an order picking tour. So this is not random. Now, random Stow would look like this, right? It's chaos. Everything is just scattered everywhere. So as long as you have a computer that's keeping track of these things, it's called a warehouse management system. I could tell you that, okay, this is the new shortest tour that visits a star and a square and a hexagon and a nuclear symbol. And you can see the length of this thing here is shorter than this thing over here. So we thought, well, okay, this is, I believe it. I look at it. It makes sense, right? You have more choices of where to go to these things. So intuitively, yeah, I believe that it helps you. And we thought, well, let's try and work out a BHH theorem for this kind of problem. This is, as you can see, I think is a generalized TSP, or it's of the same flavor as this picture I had before, because I have to pick up, one star, and the stars are located. There's 4 of them over here like that, and I had to choose which one I would visit. So we said, let's prove an asymptotic theorem that describes how this quantity scales. Now, there's some ugly integration here. I'll summarize the reasoning again. If you've taken stochastic processes, one of the core courses, you've probably seen the union bound, and that's all that's going on here. To bound this thing from below, we said, okay, how many tours are there in total? How many possible ways are there for me to do this? And sorry, I should say the following. I should say the quantities here. We'll say you have n sets of k points each. So in this picture here, I have n is equal to 6 because the numbers 1 through 6 appear, and k is equal to 4 because each number appears 4 times. And so we said, okay, how many possible choices are there? Well, there is, let me find the quantity that I want. There should be a factorial in here somewhere. Oh, I used a gamma function. What a shame. Okay, factorials visually are so much better. You know what that represents. But anyway, let me get to what I wanted here. Okay, well, this is fair enough. So what you could do is you could say, well, how many possible choices could I have? All right, and you could say, I guess I'll emphasize the important things up here. You could say I have n sets of points. Each one has cardinality k. So the total number of ways I could select a point from each set is k to the n. And then how many permutations are there? Well, it's n factorial, or gamma of n plus 1. So that's the union bound. And then we'd say, okay, what does the distribution look like of lengths on a completely random tour of this sort? And there's, like I just said, k to the n times n factorial different possible tours. And that's just a high volume Dirichlet integral. It's second year calculus in undergrad. So you can work that out using just integrals. And what that gets us is it gets us a lower bound. If you apply the union bound to this, then you can express, here's a lower bound for what this tour length has to look like. And it turns out when you do that, I'll cut to the chase here, that the scaling looks like this. So remember before I said that the traveling salesman tour scales proportionally to root n. I said it was beta times root n, where beta is 0.71. Now that scaling instead looks like square root of n on k. So in other words, if k is equal to 4, meaning each point appears 4 times, it means the tour length is going to be divided by 2. So you save half of the amount of time. And so the proof is there, but that's, we don't need to go so much through those technicalities. We did this for the non-uniform problem too, and you get a really interesting looking function here. So for the uniform case, you have this root n on k. For the non-uniform case, you have this thing. You have square root of n times k, and then times this integral. It's the square root of the distribution of these points, and then times this thing, which I'm calling p. And p is the probability that the density happens to be less than a certain value here. It's an integral over here. So it's kind of an ugly integral, but it is a closed form solution, which we were pretty happy with. So that's the one of a subset TSP. And I want to make sure I'm good with time here, so I'll wrap this up quickly. Another problem you could look at is called the cardinality constrained TSP. The cardinality constrained TSP, I'll just draw this one really quickly here. Cardinality constrained TSP looks like this. You would have a collection of points. And so let's say n is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. N is equal to 11. And let's say I give you m is equal to 5. No, let's make it bigger. Let's make it 8. The cardinality constraint TSP says find the shortest tour that visits m points. So in this case, I don't have to visit all of the points. I have to visit m of them, which in this case is 8. So that might look something like, I'm pretty sure this is not the shortest one. That's something like that. This comes useful if you're studying things like prize collecting traveling salesman problems. Like you have a bunch of points and you have to visit just a subset of them. You don't have to visit all of them. It's also comes from what's called the orienteering problem, if you're familiar with that. So we said that's another one we should study, right? No one's done a Beardwood-Halden-Hammersley theorem for this, and this seems like a useful problem. So we did that as well. And we have the convergence result here. The way we cast it is we said, assume that you have a fixed fraction of points that you have to visit. Assume that you have to visit a quarter of the points or something like that, and then look at the scaling. And so we did that there. We found that the scaling looks like square root of n times whatever that fraction is, which is not so surprising. We also did this for the non-uniform case, and you just end up looking at the square root of the distribution then times an indicator function there, which we thought was kind of nice. Cumulative TSP, last example, and then I'd love to take some questions. The cumulative TSP is not actually a subset TSP. I introduced this topic by saying that we were interested in problems where you only have to visit a subset of points. The cumulative TSP, which is also called the traveling repairman problem, is actually not a subset TSP, but it's a problem that I happen to like and that this analysis lends itself well to anyway, so I'm including it here. Cumulative TSP is a problem that looks like this. In the regular traveling salesman problem, the objective is to minimize the tour length, right? The length of this thing. The cumulative TSP says instead what you want to do is you imagine that these are customers, and rather than minimizing the tour length, let's say you start here. This is 0.0, or let's call it the origin. What you would look at is you'd say, if I am visiting these customers along a tour in the way I'm drawing here, you'd say each customer, if I'm moving at unit speed, then associated with each customer, I can have a waiting time, right? Which is how much is that customer having to sit there waiting until I show up to visit them? And that looks like the TSP. It has a lot of similar properties. You don't want to be driving a lot, but it is a different problem. So the cumulative TSP says minimize the aggregate or the average. It would be the same. The aggregate waiting time. Right, minimize the total amount of time that my customers are sitting there waiting. It is a slightly different problem. So it's also called the it's also called TRP, the traveling repairman problem. Garrett Van Ryzen and Dimitris Britsimus did some great work on this in the 90s. So we worked on that, and what we found there is that the scaling does no longer look like square root of n. It actually looks like n to the 3 halves. And when you take the non-uniform version of this, it's n to the 3 halves and then times this integral that has it has a square root of f of x like this, and then also this function p of x that I described before that talks about sort of how dense the points are relative to things that are around them. We ran some computational experiments again to verify that our predictions are sound, and there's a lot to look at here. I would say the measure of how good our predictions are is the fact that these curves more or less become flat as the number of samples increases. So what I've plotted here is I sampled for the one of a subset TSP. Sorry, I should have mentioned that. I looked for different values of different numbers of choices. And I actually did this for dimensions. I didn't label it here, but this is dimension 2 and dimension 3 and dimension 4. And so what we looked at is we said, let's plot our prediction, let's plot the lengths of these tors as the number of sets becomes large. And then we'll take the ratio of the actual length divided by our prediction, and then ignoring some other constants that arise there. And so the measure here that shows that our predictions are a good one is the fact that these plots here more or less stay flat as n becomes bigger, which is to say that our predictions are, they work well as n becomes large. So that's what I would say about those. You can ignore this clustering stuff. It's not so interesting. We also did this on a road network in Sunnyvale. So we took a bunch of census parcels in Sunnyvale, did the same kind of analysis here. And I think we have some issues with scaling because we have difficulty solving this problem for n greater than 100 for the time being, although I think we can circumvent that. Because you can see here that now there isn't this plot here is not as flat as the other ones were. You can see it kind of is increasing like this. So the hope is that if we were to bring this 100 up to 200, that you would see things kind of flatten out. And that would suggest our predictions still worked well. So we're not quite there yet, but we think that with some recalibration, we could make things happen the way we want. I included this slide in case we wanted to, in case I had extra time, but we've also applied this to a distributionally robust optimization context. I know distributionally robust optimization is, at least it was a very hot topic at Stanford not too long ago, but now it still is. You've got Yinyu Yi and Jose Blanchette there. So this I know is still a popular topic there. And actually we used, I'll just mention this briefly here. We actually used some of these continuous approximation models in a project with Nokia, which was scanning, basically they had a competitor of Google Street View, where they had to drive a bunch of vehicles throughout streets in a city. This is an image from a LiDAR scanner here. And so we actually used distributionally robust optimization, or we use these continuous approximation models in the context of distributionally robust optimization. This is Copenhagen here, to design the strategies or policies for routing these vehicles. And basically it's actually being used, or at least it was when we completed this project a few years ago. And we were pretty excited to actually have a chance to A, use continuous approximation models, and B, to use distributionally robust optimization, in industry in a practical application. So we were really excited about that. And I would love to take time for questions if you have any. So thank you very much for listening. It's been a lot of fun.
Thank you very much, John.
Thanks, Gianluca. Thank you.
I'll open up for questions. You can use the chat or simply speak up. I'm sure John wouldn't mind.
I would love to.
Maybe I'll start with one
Sure.
as an icebreaker. You talked about problems that have to do with the sidekick, for example.
Yes.
Is the problem somewhat related to a problem of optimization of, say, a network of an airline? If you look at hubs and how you
oh yes
think of transfers and so on, the problem is kind of similar, right?
Very much so. Yeah, you're looking, in fact, when people, the approach that I'm describing here is actually kind of unusual in this line of literature, that most people who study this problem are looking at it in a network structure. And you're exactly right. They identify hubs where you'd say, this is likely where you would launch a drone. Like anyone who actually is designing algorithms for solving these problems is going to take that approach. I found that, to make my life a little easier, to stack the deck in my favor, we said, let's imagine you can launch the drone anywhere. and then look at how clean the analysis is. But you're right. If you look at, if you fire up, in fact, pretty much all the work that I know of in this kind of has come from the last 5 years, 5 or 6 years. And it's almost always based on that assumption, like you said, that there's hubs that you're either implicitly or explicitly trying to locate that form the launch sites, because the problem just gets really intractable otherwise.
Very interesting.
But, that it does get this whole, in fact, the SciAm News article, I think that was how I began this, why can't I full screen here? What's going on? There it is. I think if I look at the very beginning here, I said, yes, this is actually a very important theme in my view that this perspective is good for looking at, which is a fundamental concern in the analysis of logistical systems is the trade-off between localized independent provision of goods and services versus being along a centralized infrastructure. So looking at the trade-off between something that's local and something that's very sort of global is really central to all of this. In fact, I have someone at Informs one year shared a quote from Marcelo Bielsa, who is a great soccer coach, who had a quote to this effect about how if you spread things out too much, you can't reorder the lineup, but if you don't spread out enough, the ball doesn't move around. And so someone mentioned this in a location analysis talk, and I said, oh, I need to steal this. I need to have this quote and just, throw it out every single time I can.
Very nice, very nice. Anybody has any questions? Guess it's a little late. Okay, let's see.
Xintong Yu. Hi, John. One question. Do people apply the research on the commercial situations in any difficulty? Yes. So this very last thing I was mentioning in the slide there was I had this distributionally robust optimization example. And that was a project with Nokia from maybe 2015 or so. So we used it there. And yes, there are a lot of difficulties because the math is, I think probably a lot of you are familiar with this, that sort of the cleaner the math is, the harder it is to actually make it work in practice, right? That is often the case. And so, they were describing the problem that they wanted to solve. I'll just mention quickly what they wanted to do is design a districting strategy. They said, okay, I've got a map. This case, this is Copenhagen here, and I've got some data points, and I want to design districts and assign these districts to different vehicles in a way that kind of minimizes the time until we complete all of our scans. And so when we were sort of workshopping it on the legal pads, we said, got it. Yeah, this is great. This is great. Sure. We'll do a square root of the density. That'll give a proxy for the TSP. We'll calibrate that with respect to road network driving times. And then we'll just build a weighted Voronoi partition based on that. But then when the rubber actually meets the road, there's a lot of calibration that causes problems for you. So I'll give you one example of a difficult problem that arises, or the most annoying one to me, I would say, is that the formulas that I was presenting, the convergence results, were based on either Euclidean distances or L1 or some kind of nice natural metric. And a road network typically doesn't satisfy that. And so what I've got here, this is a map of Copenhagen, as I mentioned, and I've got a heat plot that indicates how non-Euclidean or how sort of distorted the road network is. And so lighter patches mean, I think, driving is pretty simple, driving is fairly Euclidean, and then these darker patches represent places where your driving is a lot longer than what the Euclidean distance would expect. So there's a lot of calibration that happens. Like you have this basic insight or a basic understanding of how you expect to model the problem, but then when you have to account for things like my distances are not Euclidean and I'm moving along a network, and maybe I'm not actually looking at an asymptotic limit, I'm actually looking at n is equal to 25, which maybe is not the best context for this sort of thing, it can come up. But yes, it does get applied, although not very frequently, I would say. I was very excited to have this example and to have a chance to showcase it because we don't see that terribly often. Actually, sorry, one more example. Levi's Stadium in Santa Clara does this too. That's the 49ers stadium. I worked with Yin Yi, and I worked on a design of some allocation of how many people you need if you're going to deliver snacks to people who are sitting in the stands. In fact, if you go to the stadium, they have an app that you can pull out to order, popcorn to be delivered to you in the chair. And in order to reason about roughly how many people you would need, we use these kinds of formulas to understand that. And I was really sad when they had the Super Bowl that they disabled this feature. They said it was for security purposes, which made me really sad. The thought of being able to say this was, I did something that was using the Super Bowl, would have been great, but didn't happen. Great question.
Okay, any further question? I do want to make sure we finish on time. So if nothing urgent, I want to reiterate that John is certainly more than happy to answer questions offline via email. As a fellow ICME member, I'm sure there is a lot of things that he could be able to answer. But other than that, I do want to thank you, John, again for the seminar. Very, very inspiring, very interesting. The connection between sort of the classic and some of the coursework math that you showed in real problems is really inspiring, really interesting.
Thank you so much for the invitation. Really appreciate it.
Thank you very much, and looking forward to see you more.
I hope so.
On campus soon.
That would be great, wouldn't it? Fingers crossed. Thanks so much.
Exactly.
Great.
Okay. Thank you.
Take care. Bye-bye.